this is Morgan Berkeley for KI4. I am currently taking all of the classes for ECE right now, so I will be going over all the questions. Our first one is for ECE 332, and it's about a common source amplifier, and it wants to identify some of the relationships between the components and how they affect some of the amplifier features. So the first one that I did was IDS, because in my opinion a lot of the other components, when you change those, will end up changing IDS, which in turn will change most of the things that you see on the screen right now. So we know that when we change IDS, it will inversely change R out. So that's one relationship that we can see, which would in turn also change the gain. So if we change IDS, it will change the gain like inversely. So if we increase IDS by 2, it will both decrease R out by 2 and decrease the gain by 2. And due to this equation right here, we know that if we keep all of our values constant besides VSAT and we change IDS, we will end up changing VSAT by that same amount square root. So if we change IDS by 2 or 4, then we'll end up changing VSAT by 2. Like we'll increase VSAT by 2 or decrease VSAT by 2, which if we increase or decrease VSAT, we would also be increasing or decreasing the output swing that we have for our circuit. Now we're going to go to VDD, which if we change VDD and keep ID and RD constant, we will see a proportional change in VD, which would in turn change the VDS because VS is just ground, and by changing VDS, we would be pushing our circuit either further into or out of the saturation region, depending on if we're increasing or decreasing VDD. By changing VDD, we would also be changing the gain because it changes V out, and Vn would most likely stay the same. So if we increase VDD, which would increase V out, we would be increasing the gain, and vice versa. And since we know that the output gain is inversely proportional to I put it twice. We'll just ignore that last bit. Also, if we increase VDD and keep RD and V out the same, we would be increasing ID, which would in turn allow all of these things to happen. So for RD, if we increase RD and keep IDS the same, everything from the VD slide will be true, and the same would happen if we keep RD and VD the same, and everything from this IDS slide would change because of Ohm's law. So for the next question, it's a 312 question, and he gives us an output signal and 2 input signals, and the output signal is he's given us a mixer that's supposed to multiply these 2 signals given the output signal. And we have to use the Laplace and Fourier transform to find these, which I didn't put the math, but here's what they will come out to be. And then afterwards he asks us, is this mixer a linear or nonlinear element, and does this make sense regarding to its purpose? Well, I said yes. No, it is not a linear circuit, because you can see just looking at it, like when you multiply x1 and x2, it does not come out the same in the frequency domain. It's not like you're dividing it by 2. It's not even the same height or anything. So it's obviously not linear because it's not going to be carried out the same in the frequency domain. And then, does this make sense for the purpose? To me, it does, because we know that a mixer is supposed to take 2 signals and spit out a completely new frequency, not completely new signal, but completely new frequency, which we would not want a linear signal to do that, because then we would end up with the same frequency for our output signal. So for question 4, we are given this lovely picture or plot, and we want to know what it looks like when we put it in the frequency domain. and we're also supposed to label this. So for this right here is obviously the bandwidth, and it's supposed to be at omega naught. Here's a picture of it. Really, really awful grainy picture. And see how it is like shifted over to omega naught on both sides. And it has the bandwidth of 10 kilohertz for both, which is what this is supposed to be if I labeled it. And then it has half the height, which makes sense due to what our transforms look like. See how they're one half. So that's pretty much all for that one. So for questions 5, 6, and 7, I did it on MATLAB instead of putting it in my presentation. I was just going to show you the actual MATLAB code. So you're supposed to generate a Bode plot for each of us and explain why it's a low-pass filter, and how does the order filter affect the frequency slope, and approximately where is the cutoff frequency, the 3 dB cutoff point. So for that, I have my MATLAB up already. So here is problem 5, and here's my Bode plot, and you can see as n gets bigger, our filter also gets bigger. And I wrote a little code that would tell us where the 3 dB cutoff point is. So for this first one, the cutoff point is only at 9.9, and then it increases by a factor of 100 for each one. Like for each n, it will increase by a factor of 100. Here's what it looks like. And you can tell that it's a low pass filter because anything past that 3 dB cutoff point will not go through, just as you can see in this plot. Now for question 6, it says now consider a new filter given by substituting as GS and generate its Bode plot. What type of filter is GS? And explain. Well, for number 6, here's my plot. And it's obvious that it's a high-pass filter now. You can tell because it's exactly opposite of our low-pass filter, right? And then our 3 dB cutoff is, even though I don't have a line for this one, is obviously around 10 to the negative 3. Okay. Right? And then for question 7, it says a band-pass filter, or how can you use one low-pass filter and one high-pass filter to build a band-pass filter? And use a sketch of the Bode plots to illustrate your approach. And for this one, I originally did it by hand, but for all intents and purposes, I did it in MATLAB for this one as well. I just combined the two above photos or plots into one plot to show you what this band pass filter would look like. There you go, right? So that's what it looked like. Basically, you just want to have to run the low pass filter first, so you make sure that you don't cut off everything that's supposed to be in the high pass filter, and then you run that high pass filter, so then you get both of them on the same. If you can get both of them in there. And that's what it looks like. So beautiful. Alright, now for question 8, it's an electromagnetics question. Based on what you know from electromagnetic wave attenuation, discuss what would be the influence of different weather conditions on signal transmission and reception. So we know that weather conditions can affect the humidity in the air, which can affect epsilon and mu, which is the electric permittivity and electric permeability, and that can obviously affect our signals. And snow and dust and fog will also have similar effects in this situation. For question 9, we have this lovely dipole antenna, and for this, it's just asking how we would align both like the receiver and the transmitter. And I said you would want to align them in the same direction because in order for the antenna to receive the full power of the signal, we know it has to be completely aligned. And we know this from Faraday's law because it has to take the two cross products of it, and the cross product of an orthogonal signal in reference to the receiver would just be 0. So obviously we would want it to be directly like um, oriented in the same direction in order to get that full power. Now for question 10, you just had to review different antenna configurations that will generate different radiation patterns and discuss the possible applications of these antennas. So for this one, I accidentally lost the page where I was supposed to do it, so I kind of just did this off of memory. And I remember monopoles antennas, these have really no gains, and they broadcast in all directions. They have very, very broad broadcasting. And for hemispherical antennas, these can receive signals from 0 to 180 degrees, which is very, very useful because you won't be getting any signals that bounce off the ground. You're just getting the signals that you want. So it's kind of like a dome-shaped kind of antenna. And then array antennas is just a very general one. It's just composed of multiple different antennas that are used as one single antenna. And these are very useful because they usually give us a higher gain than our monopole antennas that only have one antenna. So that's also a very useful antenna. Now for question 11, discuss the typical size, order, magnitude that an antenna must have for different carrier frequencies ranging from 100 kilohertz to 100 megahertz. So for this one, I adjusted 100 kilohertz and 100 megahertz for the example. And I said typically the antenna is approximately 1/4 to half of the wavelength of the antenna, or like the size of the antenna is supposed to be, just forget that one word. So if our frequency is 100 kilohertz, then our antenna would have to be 700 meters. It makes sense. Well, for me, I did for quarter of the wavelength, so it would be 700 meters. Now, if our frequency is 100 megahertz, our antenna would be much, much smaller. It would only have to be 0.75 meters. So it's crazy small. So we can see that the larger the frequency, the smaller the antenna would be, and it changes proportionally. So for our last question, I just have like a picture over here that I can show you. So for this, we all know this lovely picture. I'm just going to kind of just discuss what happens for it. So we get our lovely signal, which would probably be this little, oh, there you go. It'd be a nice little sign coming through here. That's a really awful sign, but you get the picture. It'd be a nice little sign coming through the amp, like through here. And then once it hits this amplitude, it would go from being whatever this is to, well, let's say like 10 times as big. So it would just be like a giant signal, right? And then goes through this mixer plus this low frequency right here, and we will get something similar to, okay, we get something similar to this, right? This is what they showed us in class, like a nice weird little thing, right? And then once we go this amplifier right here, it will have that same exact picture as this, but it would be amplified to whatever that power was. And then we would go through this bandpass filter, which would hopefully attenuate all that noise that we don't want. And then we go through this lovely diplexer, which would tell us whether or not we're receiving or transmitting, and then I'll go to the antenna. And then that's pretty much all. Well, thank you for watching. I'm sorry for it being so long, and have a great day.